Okay, so welcome guys. So in this video, I want to prove another very famous theory in the computational complexity in a very abstract way. So these proofs are not 100% rigorous. There are some subtlety here, right? But in this video, I just want to give you guys a feeling, and hopefully you guys can understand something in this very short video. Okay, so the very famous theorem is called the time hierarchy theorem. Okay, so the intuition in the way is that if you're like a math people like me, then the first question, the answer, the naive question is that are there problems which are more difficult than others? So it's like a very, the answer should be yes, right? So it's very obvious that when you learn the junior high school, then you know how to solve this uh, quadratic equation. So the idea is that people will think that solve quadratic should be more difficult, more difficult than solving linear, like ax plus b equals 0. So I think that people believe that there are some problems which are definitely difficult than others. So it means that there are some problems if you solve by computer, then you should solve it by it should or can only there should be some problem which you can only solve by using much more time. Okay, so the answer should be yes, and then there should be some language L, which you can only need t2n time to solve it, but you cannot solve it by t1n time. So the idea is that let's choose t1n, which is some function of t1 is just time, some time function with the number length of input t1, and also some time t2 function, which t2 is very larger than t1. And we want to prove that there is a function, there is a language L, or later it is a problem, such that if you want to solve this problem can only be solved by t2n, but not t1n. Okay, so ideally, this is an intuitive answer, right? But how to prove this it's very tricky. Okay, the proof idea is that so we already know that a set of all Turing machines is 1 1 onto to the finite bit string, right? So finite bit string is isomorphic to n. So I use this bracket. So this bracket will change if I give you a bit string, finite bit string, and you can change this. You can use this bracket to change it to Turing machine. Basically, I give you input like a bit string like 0 1 0 1 1 1 1 1, and you can change it into Turing machine. And we already use set theory. If you know about set theory, then this statement is somehow very trivial. Okay, so the proof idea is that let's define L via some t to n. I think we don't need this statement. Okay, so the idea is that we define a Turing machine D, which will take input x. So x is a bit string, right? So this is input. So the idea is that we define a Turing machine D x on x, then m to be x bracket. So that means we first change this x into another Turing machine. So I call it m. Okay, so then m be x, and then we will simulate mx. So we will simulate x. So x you can view. So m is, you remember that m is like a Turing machine transformation of original x. So mx for let's say t1 point n of time. So t1 point n is basically some function which is greater or equal to a very larger than t1n, but still less than t2n. And after t1 point from n of time, then we do the opposite of m. So the idea is that if m reject, then d will accept. If m accept, d will reject. So the idea is that if m output 0, then d will output 1. If m output 1, then d will output 0. And if m do not halt, if m does not halt, then d just output 1. Actually, nobody cares. Okay, and we assume that all of these steps d can run in t to n. So basically, d always halts in t to n of time. So that's why I assume that t to n is very larger than the t1. Okay, so this language is in the t to n. So we define the language we define L to be a language decided by D. So basically, if you don't know the terminology, this means that L is the answer Y. Like say D of Y is 1. Basically, I collect all the language which make D output true, and collect this set of string and call it L. Okay, so now we want to show that there is no Turing machine T1 and Tm can decide L. So that means I want to prove that for every Turing machine which only runs in T1 and cannot decide L. So that means there should be some string which this Turing machine and the D give the different answer. Okay, so this is some of the diagonalization trick. So let's Q be a Turing machine runs in T1 enough time. So let's Q be our candidate. So right, we know I already know Q is a Turing machine. So let's write down. So Q is a Turing machine, right? So there should be some bit string representation. So I call it X. So for some bit string orientation X, bit string representation X, and represent it as a Q. So I define this. Okay, so we know that Q of X will finish T1 X of time. Basically less than T1 X. Now D of X finish the simulation. Okay. So we see D of X will take this X as right. So now X is Q, right? So D will run Q of X. So D will finish the simulation, but did the opposite of Q. Okay, so now D of X will not the same as Q of X, because if Q rejects, then D accept. If Q accept, D reject. So Q does not decide L, right? Because Q and D and Q, they at least makes different, have the different result on X. So that means Q does not correctly decide L. Okay, so that means any T1n time machine cannot decide this L. So that means L do not belong to time T1n. Okay, so this is a very high level proof. And in order to prove this in a very detail, you need to consider big O, and also some subtleties. But the idea is just this. Okay, so I think this is the second theorem I learned in the complexity theory. The first theorem is people like to talk about is the halting problem. So halting problem is not decidable. And the second problem, very amazingly in the complexity theory, is called the time hierarchy theorem. So I hope you guys understand what I'm talking about and enjoy this video. Okay, I will see you guys in the next video.